There's a whole class of data problems where the most important questions begin with time. I'll give you my most heart-stopping example. The server crashed at 3 a.m. So what happened at 2:59? Or a happier example, we always make more sales on a Friday, but when should we start scaling up to handle the load? Time is often the first criteria you pick when you're answering data questions. And if you've got a lot of data, you can easily be looking for a specific time range in several billion rows. And that kind of thing doesn't scale trivially. So for a time-centric data set, time-centric queries, it starts to make sense to look at a time-centric database, or a time series database, to use the jargon. But how do you build one of those? What makes a database a time series database? It's an interesting engineering problem. So I asked an expert. I asked Paul Dix of InfluxDB to come along and explain how you build a time series database. And happily, he goes into great detail about the ins and outs of it, things like time-structured merge trees and what they are. And then we get into some juicy questions that I wasn't expecting answers to, like, what happens if you build some technology that your customers like, but you think you need to do a massive rewrite if it's going to grow? What do you do if you get the technology right, but you get the pricing model wrong and you have to course correct on that? Or what if everything's so successful that you get pulled into management when really you kind of wanted to stay writing code? I got talking to Paul about all of that, and unusually for a CTO coming out of Silicon Valley, he was incredibly straightforward about the mistakes as well as the successes. He's very frank about what he had to learn the hard way, things you'd like to know before you go down that road. Things from, should we write it in Go or Rust, to what happens when the logical pricing model is the wrong one, to the pros and cons of using Parquet files. If you're interested in how databases get built, there's a lot here. And if you're interested in the problems you face when the technology becomes a whole business, there's even more. I'm your host, Chris Jenkins. This is Developer Voices, and today's voice is Paul Dix. Joining me today is Paul Dix. Paul, how are you?
I'm good. How are you?
Very well. Glad to see you coming in from New York City.
I am in Williamsburg in Brooklyn.
In Brooklyn. Do you know, New York is... I live in London. New York is the only place I've been to in the world that has genuinely overwhelmed me.
Really?
Yeah.
Coming from London.
Coming from London, I showed up in time... The first time I went there, I showed up in Times Square, and I came out of the underground, the subway, and I looked out and I go, oh my God, this is big.
I mean, Times Square is a bit overwhelming. Most New Yorkers actually avoid Times Square, so...
Just a tourist thing, huh?
Yeah. Well, I mean, I assume, like, are you dropping into Piccadilly all the time?
Yeah. Okay. Yeah, that's fair. So I'm going to try and thread the needle here from overwhelming the senses with being overwhelmed by too much data. Let's talk about time series.
Nice. It's a little thin, but sure. Let's get into
We'll just
series.
Cross any bridge that's available. We'll go with that. So you're the CTO of Influx, one of the co-creators of InfluxDB, right?
Yes. Yeah. So I'm the co-founder and CTO of Influx Data is the company, and InfluxDB is the project, right? So I was the founding CEO, and after about 3 years, I hired in my replacement, Evan Kaplan, who's now the CEO, and we still work together today.
Nice. Nice. It's not always a relationship that goes well.
Yeah. No. I mean, it's had its ups and downs, but it's been really great over the years. So.
Okay. I want to get into this because you seem to have spent a decent part of your kind of Silicon Valley-esque tech management career avoiding being sucked all the way into management and keeping your hands on the tech. But we'll get there.
But first time series.
Yes. Okay, so I want to start this from the naive point of view, and you can wise me up. Up to a certain number of rows, I reckon, let's keep a small number, let's say 10,000 rows, I can stick 10,000 rows in Postgres, create an index and a time column, and I am happy and no one can tell me different. So at what point, what is it the time series database does that doesn't? Is it just scale, or is it something interesting elsewise?
Yeah. So, I mean, this is funny. Like, I talked about this the very first time I gave a talk on InfluxDB. It was literally the thing I said. I was like, you've got a relational database, you've got a time column, just index by that, slap a time column on it, or, organize by that, and there you go. And scale is obviously the first problem, right? When you think about relational databases and OLTP databases, transactional databases, they're inherently designed to handle a certain amount of scale, right? And they're, that's for bank transactions, for purchases on an e-commerce website, and all, save for, but like, a handful, a few dozen companies, most people don't have to deal with a transactional workload scale that is too crazy, right? They certainly don't have to deal with a billion rows a day getting written into the database, right? Now, of course, if you're Amazon, that's not true. If you're Stripe, that's not true, right? And they have all sorts of specialized stuff to deal with that. But from a database perspective, most transactional databases are not designed to handle a billion rows a day getting written into the database. And trying to organize that data. And in the time series use case, a billion rows in a day really isn't that much data, right? Like so backing up, what is a time series? What is time series data and what is a time series database, right? So time series data is really just, at its simplest level, a collection of time value pairs ordered by time, right? And then the thing that adds a bunch of complexity and the values could be whatever it is you're measuring, right? They could be floats, bools, integers, there could be strings, they could just be raw bytes, but it's basically some piece of data that you're organizing by time. And then
I'm just going to pause you quickly there. So you're implying it's always primitives rather than structured objects.
Well, so then you layer structured on top, right? So the primitive, the absolute like core primitive is some kind of value and a timestamp and the ordering, right? The time-based ordering.
Right.
The structure you layer on top, most time series databases have something called either tags or labels in Prometheus, right? Which basically attach metadata to all of this time series, right?
Okay.
So, but realistically, like the way I view time series is, to me, time series is basically just a way of representing data, and any database can give you back a time series, right? You can query against the data, and as long as you have time-stamped data, you can query it back and represent it over time, right? And a lot of people, when they think about time series, they think about metrics, which are basically pre-computed time series, right? You say you're going to take samples every 10 seconds or every minute. You're going to measure a thing. It could be an average, it could be a percentile, it could be a count, it could be something else. You're going to measure that thing and you're going to attach a bunch of metadata to it. And then you store that, and then you want to query against that. So in its purest sense, a lot of people think that's what a time series database is. And to some extent it is, but in my mind, you can pull time series out of really any kind of observational data that you can think of, right? If you take a bunch of log files, you could produce on the fly basically an infinite number of time series out of a bunch of log files, right? If you had like an Apache log, it could be request to a specific page, it could be 200s, 400s, requests from specific addresses, from specific users, rolled up on all sorts of different levels, like by different geographies, right? There are a bunch of different ways you can slice and dice this data, but the end result is what you're looking at is something that's changing or not changing over time, right? And you're doing this generally because you want to either put it on a graph so a human being can look at it, or you want to build a monitoring system that looks for some sort of change that is important, that's going to trigger either an alert to a human being, or it's going to trigger some change in a system, some automation that you're doing, right? And server monitoring is the easiest one for people to think of, for programmers to think of, right? So if you think of like, you're operating a service inside of Kubernetes and you want to scale up the number of containers or scale down the number of containers. What you'll do is you'll track a number of metrics that represent kind of the load on the system, read or whatever you want to track. And then you have the automation look for the change and then trigger up the scale up or the scale down based on that. Right.
So that's interesting. Does that imply there's like some kind of push-based streaming in the database, or are you just saying make it fast enough that you can poll that query over and over?
So both approaches are valid. And I've worked with time series data where we've tried both. Like before InfluxDB, I worked for a fintech startup and we were doing like real-time pricing in the corporate bond market and all sorts of other stuff. And the original solution we had was a push-based model where people connect to the database and subscribe to these are the things I want to listen to, and it would push it out. And actually what we found was that was terrible in terms of performance and scalability. It was great in terms of like guaranteed latency, or not even guaranteed, like average latency of getting a notification, but a much better way to structure the whole thing from operations, reliability, scalability, and predictability kind of standpoint was actually a polling model, right? This was a case where we didn't need, everybody talks about like real time, which I put in air quotes because real time is highly dependent on context, right? If you're tracking, say, the temperature changes for some massive boiler, real time on that thing, like the temperatures don't change that fast because it's this huge boil, it's this huge thing that's just like, if you monitor that once every, 10 milliseconds, it's not going to matter. Like, you can take a measurement every 10 minutes and you're totally fine, right? And real time is also dependent on like what's going to happen, right? If you're triggering an alert to a human being, if you take 100 milliseconds to trigger that alert or 5 seconds, generally it doesn't really matter if it's going to a human because their response time is going to dominate, right? The time of the system is not going to matter. But if you look at use cases like high frequency trading, where they're making trading decisions, right? One, they don't use like commercial time series database solutions, right? That's essentially it's to every single one. They like custom write their own stuff because their expectations is like, we have to like get these events and respond to these events in like less than 50 microseconds, right? Yeah. So their perception of what constitutes real time is very, very different. So it's all like use case dependent, and it also depends on like where you're collecting the data and what you're doing. I think that's actually going to become a lot more obvious when people look at use cases in like robotics, right? Where in some cases, like you need the database and the collection and the actual action very, very close to the physical system that's operating versus, a cloud-based solution for server monitoring where it doesn't matter if you're going across half a continent, you're going from, the West Coast of the United States to the East Coast to send your data because a server monitoring system doesn't need to respond in the tens of milliseconds that robotic systems need to respond in, for example.
Yeah.
So this is all getting pretty far afield from the original question, which is what is time series data? What is a time series database? So why a time series database? So scale is the most obvious one, right? There's that. There's basically a set of queries that you want to do. Like time series queries are almost always, there's two kinds of time series queries. One, which is not really a time series, which is get me whatever the last value measured was for this sensor or this collection of sensors, right? And that's something you kind of want to optimize for. And then there's another, which is show me, get me the time series data for this sensor or what are these collections of sensors. And either you want just the raw data or you want to compute some sort of summary against it, right? The summary could be the average, the P99, or you could want like, the min, the max, the mean, like all of those to come back. And essentially like in our use cases, almost always people want those to come back within tens of milliseconds or hundreds of milliseconds at most, right? These are not analytical report style queries where you're okay with it taking tens of seconds or minutes to go, right? Like where you like submit a job and it runs in this background system and it takes forever, right? The expectations in our use cases of time series, which are a lot of sensor analytics, server monitoring, custom metrics, network telemetry, satellites, rockets, like all these things, their expectation is they can write the data in and within hundreds of milliseconds, it is queryable. And then when they query it, those queries return, like many of those queries, most of those queries return in tens of milliseconds or hundreds of milliseconds.
Yeah,
and again,
that
that's
threshold
all,
where for a human, it's like you can't tell the difference between it being instant.
yes, exactly. Yeah. That's all driven, by the kind of like user experience that you want to have within your app or within your dashboarding solution, or driven by your monitoring system where, you have all these queries operating. So, and I would say like a lot of monitoring systems operate on this basically polling model, right? You have like this condition that you're checking for, and you just choose a frequency on which to check for it, right? And usually so if you're checking for something once every 10 seconds or once a minute, right? Usually what you're doing is you're actually checking for something recent, but you're not just checking for, a lot of times, like that last 10-second period or that last minute period. What you're actually doing is you're querying a little bit further back in time so you can get a little bit more context, right, to say like what's going on, right? So you're not just querying like a point in time, you're actually querying a range, and it's a moving range of time of like, give me the last 5 minutes worth of data for this thing so I can run some computation and see if there's something I'm looking for. But
if the CPU is over 90%, then show me what it was doing for the past 5 minutes so I can understand what's happened as it's leading up to 90%.
Yeah, and those monitoring and alerting queries, a lot of times those will represent more of the query workload in a production system than all the other queries combined, right? The other queries are basically, usually they're like dashboards that people are looking at that are refreshing on an interval, right? Usually in the refresh interval is 1 second, 5 seconds, 10 seconds, 30 seconds, maybe at most.
Okay, so take me under the hood. Does this mean that you've got a kind of two-part architecture, one that's dealing with the hot set and one that's dealing with the archive stuff on disk?
Ideally, yeah. Like, because of the performance expectations, you expect the hot set to be in RAM, but keeping that data in RAM is super expensive, right? RAM is the most expensive place you can put it. And the other kind of like problem about this is that the hot set that you have is constantly changing, right? It is like, it's basically like, there are only two hard problems in computer science: naming things and cache invalidation. And basically this is like constant cache invalidation. Your cache gets invalidated literally every second as new data is coming in. Yeah. So there's the scale piece, which is just the volume of data. But then the other piece is this managing of the data lifecycle between getting it in and putting it in RAM so it's fast for query, and moving it off to either a locally attached disk or object storage, ideally, right? Because object storage is now, it is essentially the de facto place where people are going to store data, and it's like cheap and scalable and all this other stuff. But then you need to also manage, are you going to use local disks for caching data? And if you're going to do that, how do you move data in and out of that local disk cache and make the whole thing efficient? So, and then other pieces of this use case are, there's, do you want some built-in downsampling? So it's very common to, collect very high precision data, and the value of that data as it's recent is much, much higher than as it gets older. And as it gets older, you maybe don't need the same level of precision.
Oh, yeah. So if you're getting data every 10 milliseconds, eventually when it gets to like a year old, you only care about every 10 seconds.
Right. Or minute or hourly, right?
Yeah.
Like, exactly.
That makes sense.
Basically what that means is, like, if you're collecting every 10 seconds and you change it to 1 minute summaries, you're reducing the amount of data you need to worry about by a factor of 6, right? Usually that's actually not quite the case, because people will keep multiple summaries. So you don't quite get that clean of a, reduction. But usually I think what people do is they'll have 1 minute summaries or 5 minute summaries or 10 or 15 minute summaries. And then 1 hour summaries is basically like the last tier, right?
Yeah, you're making me, because I was expecting the technical meat of this to be actually a B-tree index won't cut it. We need specialized time-based indexes. But you're making it sound like actually the biggest part of the implementation challenge is kind of data logistics, like just managing that data in different ways.
So there's that. There's also the underlying file structure, right? For InfluxDB 1, we wrote our own storage engine from scratch to be able to deal with this. And again, the reason for that is one of the things that makes the time series use case so tricky is your data arrives, what I would like to say, like wide, right? Basically, you have a single data point for a single point. You have now data arriving, but whenever you query, you're not querying just now, right? You're querying down, like this is the wide, you're querying deep, right? So when you query, you're saying like, I want, the data for this sensor or an aggregation across this group of sensors for the last 24 hours, right? So the data arrives like this, but you're querying like this. And the trick is, how do you optimize for that? Right? Because if the data arrives like this, the easiest thing you could do is like, we're just going to append it to files, and we're going to create new files. And basically, like, say we just like open up a file every 10 minutes and we append the data into it. And then once the 10 minutes is done, we write that file to disk, or we write it to object storage, right? And we kill the log for that. And then we just keep going. And then but the problem, and you can scale infinitely there, and it's great, and you can ingest all the data, and it's super cheap. And then the second you try to query it, the query is just going to be unbelievably slow, right? Because then to query it, you're going to look at the time, and then you're going to say, okay, I have every 10-minute file for that block of time, but then you have to churn through all of it. So the trick is, you have your data arriving like that, and you need to reorganize the data on disk so that you can query quickly to that, right? And in some sense, it's an indexing problem. But as anybody who's worked with indexes in a database knows, like, the more indexes you add and the higher the throughput the table is, the more painful it becomes, right? You end up using more RAM and like more CPU to like maintain this index. And like, so those are the problems, right? So it's very much like a data lifecycle logistics problem, but it's like, the storage system that you end up designing for it is very, very different, I think, than, let's just use a B tree. Like, actually in version 0.9 of InfluxDB, version 0.8 of InfluxDB, we were using LevelDB, which is a LSM tree built by Google, open source. RocksDB was a popular fork of it that was created around that time, that was at Facebook. So in version 0.9, we switched over to a B+ tree, a copy on write B+ tree called BoltDB, written by Ben Johnson, because it was written in Go at the time. This is like great, like rock solid implementation, whatever, but the performance of it was absolutely abysmal. Like, it did not work for this, which is what led us to creating our own storage engine that was essentially like, the storage engine we built is called the TSM tree. So it's time structured merge tree. And the reason we called it that is because it's inspired by the LSM tree. It's like the LSM tree, but it's optimized for this specific time series use case.
Can you explain how it works? Without the use of diagrams.
Just waving my hands around.
No, you can't even do that, because this is on Spotify as well.
Oh God! All right. So that version of the database is I've said this before. It's actually like two databases in one, right? So the first part is basically the time series part of the database, and that's that TSM tree thing, right? So essentially, you write data in. It goes into a write-ahead log, and we also keep it in RAM in a different format so that it's fast for query, right? And then periodically, what we will do is we will snapshot all of the stuff that's in RAM into a TSM file, right? So basically, like, this is like the first level, is this snapshotted TSM file.
Right.
And then in the background, and basically all the data in the snapshotted TSM file is organized by time value pairs, where we've taken the data model for InfluxDB is, you have a measurement, you have a database. In version 1, you had something also called a retention policy, which I could talk about in a second, but think of those as like one concept. You have this organizational bucket called database and a retention policy. Within that, you have measurements, and measurements have rows, and each row has a tag set, which are key value pairs of strings, fields, which can be int, bool, float, or string, and then you have a timestamp, right?
Okay.
And basically, an individual time series is basically the measurement name, the tag set, and the field name, right? And so basically, if you have that identifier, you will then have a value and a time. That's a single capture, right? And then, So what we do is we organize in the underlying storage engine, we give the measurement name, tag set, and the field name like a UN64 identifier. And then we organize that data in the TSM file by that ID, which is the time series, and then value time pairs sorted by time, right?
Okay.
And so basically when we write that file, we organize all the data by that. And within the value time pairs sorted by time, we break them down into blocks of 1,000. And the reason we do that is so that we can apply compression to that block, right? So we compress the timestamps separately from the values. So the timestamp compression uses zigzag run length encoding. It's basically kind of like a form of double delta encoding. And then the value block gets compressed based on the data type, right? So is it a float? If it's a float, we use the Gorilla style compression that Facebook had written about back in whenever that was, 2014. Right. If it's an int, we use the double delta run length encoding. If it's a string, we use snappy compression.
That's interesting that you're actually being that granular about the types of compression.
Yeah. Any analytic file format will actually do that same kind of thing, right? Parquet does this. It has compression for the different types. The latest bit that people are trying to do with new file formats is basically how to decouple the actual file format from the fact that you can have different kinds of encodings and different compression schemes, and kind of how do you decouple those two? Anyway, that's a different subject, not for this.
Right.
But so then the other part of the database structure is an inverted index, right? So usually you use an inverted index in document search, right, where you have documents which have an identifier, right, like an in64 or UN64 identifier, and then you have the terms in the document, and basically the terms map which terms appear in which document, right? So you have a term like the word developer, and you say, okay, now you have a posting list for which documents that term appears in, and the posting list is basically just the IDs sorted by the ID number, right?
This is the one that looks most like the index in the book, right? Where you look up the word developer and it tells you the page numbers.
Yeah. So then what that means is you can do set operations on it, right? So if you say I want to search for documents that have developer voices, right? Both developer and voices in it, then you get the two posting lists, you do an intersection, and then you have the set of document IDs that those appear, right? Okay. Great. So the thing we did was we realized, well, the metadata that describes time series could be represented in an inverted index. Right. So that's the tag set, right? The measurement name, the tag set, and the field name. So the tag set is, remember, the key value pair. So it could be in server monitoring, it could be the region, the availability zone, the host name, the service it came from, all sorts of things like that. Yeah. And basically what that means is, so when we're ingesting the data, we create this inverted index, and that's a separate file that gets created. So we call this the TSI, time series index. Initially, when we built the TSM tree, this inverted index was entirely in RAM, and we would build it on the fly when the server started up, right? Basically, when the server started up, we would look at all the TSM data, and we would actually build that inverted index on the fly. So, and this was true basically for the first year, from 1.0 of InfluxDB, which was in September 2016, to version, I think it's 1.1. I think it was a release in November of 2015, or 2017, that had the disk-based indexing, right? So essentially what that means is you have an index where you say, okay, this tag host A has these time series that it maps to, and region West has these time series that it maps to, and like whatever the tags are that you represented. So when a query comes in, we look at what measurement are you selecting from. You can think of a measurement like a table in a SQL database, and tags and fields and time, those are just columns. They're columns of specific like types. So then we look at the where clause of the query, and we look at the tags that you have in it, right? So we say, we look at those tags, and we look up the posting list for the measurement name. We look up the posting list for the tag key value pairs, and we do intersections or unions depending on what the structure of the where clause looks like, what the predicate looks like. Are you saying and, or whatever, right?
Yeah.
So basically we look at the inverted index to get the set of time series IDs. And then we go to the TSM structure to look up this ID, this time range, give me the data, right? And the TSM structure is, like I said, what happens is that data arrives as a file. And the thing I haven't talked about is the compaction process, right? So the problem, this is basically the trickiest part of the whole thing, right? All this other stuff is like easy. The trickiest part is that, you get this set of data and say, we're going to like snapshot, 10 minutes worth of data.
Yeah.
And what we're going to do is we're going to write one TSM file for that 10-minute period. And then we're also going to write an index file. And the problem then is in the background, what we have to do is we have to combine the index file and the TSM file with other regions of time, right? So we basically, like, if we captured this 10-minute window of time, what we want to do is say once an hour, we want to rewrite the 6 10-minute windows into a 1-hour block, right? And I'm simplifying it because it doesn't actually work like this. The problem is, like, in InfluxDB, you can actually like load data for any point in time. So it's not guaranteed that the 10-minute window of writes that you just captured are actually for the data that describes that 10-minute period of time. The timestamps on the data could be for any period of time. So
there's no guarantee that the data arrives in time order. Like some data will show up a bit slow, even though
that's right.
Like a sensor that only connects to the internet once an hour may have an hour's worth of backlog data.
There's that. There's like the server could go down. The thing that's collecting the data could slow down for some reason, right? There's always lagged data collection, even in a system that is like, performing well. There's going to be some delta of, some writers and some collectors are not exactly in time with the others, right? You're not going to have a strict time ordering of the data coming in. Like if you did, this problem would be a lot easier. It'd still be hard, but it'd be easier. So basically what you have to do is, right, we're going from the 10-minute to an hour. We're going to take the 10-minute blocks of time and rewrite them into an hour block of time. And it could be many files that represent all this, but we're going to rewrite them. And what we're doing is we're rewriting them so that the data is now organized by series time value pairs, right? So think about data where you're sampling once every 10 minutes. In a 10-minute window of time, you are going to have 10 samples, right?
When you're sampling every minute.
When you're sampling every minute.
Yeah.
Right? So you're going to have 10 samples.
Okay.
And basically what that means is your compression is only going to work against 10 samples, right? Because again, we're organized by the time series and the thing, and we block it by time series. And it also means if you go to query, what you're going to do if you're querying an hour's worth of data and you haven't reorganized the data is you're going to touch 6 files, right? You're going to have to look up in each of those files where that time series is. You're going to have to decompress the blocks. You're going to decompress 6 separate blocks, and then you're going to merge that up and send it back to the user, right? Yeah. Now, that's fine for just an hour, but as you get into longer and longer time ranges, it becomes slower and slower. So the point is, we're going to reorganize it so that once an hour, we're going to take those 10-minute blocks of time and we're going to shuffle all the data. So what it means is you are literally rewriting every piece of data that you received in the last hour and rewriting it into new files. So, but what that means then is when the query comes in, you have one index that you reference for that 1 hour block of time rather than the 6 different indexes that you reference. So one index that you reference, you find the time series in the one place where it is, and you get the 60 samples and you send it back, right?
Yeah.
So basically what you did there is you made it so your query had to do a sixth of the work. Right before, when the query came in, you had to reference 6 separate indexes and look at 6 separate files and decompress the data and send it back. Here, now, because you've just reorganized the data for the hour, when you query that hour, you only have one index, one file.
Yeah. So you've amortized the cost of merging that query out, right?
Yes.
Yeah.
Yeah. So that process of rewriting the data is called compaction, right? So again, like that is part of the TSM tree, and we took inspiration from log structure merge trees, right? Because compaction is very much a part of the log structure merge tree. So one of the other things we did was we created what we call shards of data, which are basically just windows of time. So essentially, like by default in InfluxDB 1 and 2, a shard of data is 7 days, right? Okay. And what that means is you can write data for any period of time, but if it comes in, we will split it out into the separate shards that it belongs in. And what that does is it kind of like ring fences the amount of work that the compactor will have to do. And it also means, even though you can load data for any period of time, the most common thing in our use case is people are loading data roughly for now, modulo some collection lag or whatever, which usually is measured in minutes or hours at worst.
Yeah.
Right. Even people who have sensors that only connect once every 12 hours, like your collection lag is going to be like 12 hours. Right.
Yeah,
so, but what that means is a shard after a period of time will become what we call cold. It's not receiving any more writes anymore. And then what that means is what we can do under the hood is we can do what's called like a full compaction, where we say, okay, we don't think this period of time is going to get more writes. So we can spend a little bit of extra effort to do a complete rewrite, a reorganization of the whole thing. Now, in many cases, like the full compaction actually doesn't result in all of it getting rewritten because there are like various levels and like other things have happened. And like this shard is not kept in like one file, right? It's kept in potentially tens, hundreds, or thousands of files. So we do the full compaction. And basically what that means is there are entire swaths of the database, the historical data, where the database, the operational part of the database can just ignore it. Right. It doesn't have to worry about, do I need to compact it? Right. This goes back to the cache invalidation thing, which is like you have a flag on those old shards that says whether or not they received a write. And then you can say like, okay, now I need to look at it again and see if I need to reorganize the data.
So what you've done overall, as you said, we'll take 10-minute snapshots because that's a sensible amount of data to snapshot quickly and move on. But now we've also put an upper bound on how often we'll re-merge this for performance.
Yeah.
Yeah.
That's a lot. That's pretty massively simplified from how it actually works under the covers. That it doesn't work exactly like that, but that's basically like the structure.
I'll take the logical model. I don't think we need to get into actual writing bytes.
Well, the other thing is, like, I haven't looked at that particular bit of code in many years, so all of this is from my faulty memory.
It seems pretty warm in the cache, I have to say. I wonder if there's anyone else in the tech department at Influx screaming, "It doesn't work like that," in their head.
Maybe not.
You'll find out after this goes live.
Yeah.
I was wondering, as you were explaining that, do you have any transactional problems on these TSM files, or have you just got like a single writer dealing with, I write this stuff out, I write the new compacted version and swap over?
Yeah, we have a single write.
Single writer.
Yeah. So basically when the swap happens, essentially there's like, there's a there's always like a write ahead log that captures the operations, and then there's an in-memory structure that is protected by a mutex that we swap over. So
okay.
And the other thing is like for the storage engine, there's logic under the hood to basically do like deduplication of the data as you read it, right? So as I mentioned, like you can write data to a time series for any period of time, but the data, the rows in a table, so measurement, the line, we have a protocol called line protocol, which is basically like you're writing like rows of data into specific measurements. The rows are identified by the tag set and the timestamp, right? You can think of that as kind of like the primary key.
Yeah.
So one thing is people can like overwrite existing values, or they can overwrite the same tag set and timestamp with updates or additional fields or whatever. And under the covers, what we have is stuff that will combine the data from multiple TSM files into one merged, deduplicated stream, right? So it means that one of the nice properties of the database is like you can, if the writer is providing the timestamp, which is what we recommend for the data, then you can essentially like just retry it if there's any sort of failure, and not worry about duplicates and stuff like that. Like the database dedupes everything for you.
Yeah. So yeah, you can. It's kind of idempotent, right? Eventually, if I send the same data over and over, it will boil down to a single value.
Yeah. It also means you can do things like upserts and stuff like that, which some people do. It's a little weird because, ultimately, like that has to be handled by the compactor. So if you're like changing or updating data or whatever, it does mean like the compactor is going to have to do some work on the back end to reorganize it for you. So there's, it all depends. Like some workloads are more expensive than others based on the work you have to do.
Yeah. Does that mean you're capturing two timestamps, the kind of logical one that the user provides and the timestamp it actually arrived, to find out which is the newest? Or are you just saying whatever's newest in the write-ahead log wins?
Whatever's newest in the write-ahead log, and then the actual TSM files that get written to disk are ordered, right?
Okay.
So we don't use timestamps for those. We actually just use like sequence numbers because clocks are liars and can't be trusted. But
okay, you've preempted my next question. So yeah, okay, I start to see the shape of this. I think so. So you've gone through 3 versions, and you've been deliberately leaning on versions 1 and 2. How has it evolved from that logical model?
Yeah, so version 1 was the time series merge tree and then TSI. Version 2, we used the same core database technology, but then we added our own scripting and query language called Flux. We added, a bunch of stuff around the edges of the database. We launched like a multi-tenant usage-based SaaS service, which I can tell you all sorts of nightmares about doing multi-tenancy in databases, and how I can tell you about the right way to do it and the wrong way to do it. Sadly, I've done it the wrong way before, so
I think we might get into that.
And then for version 3, because I'm a sadist addicted to pain, I decided it would be a good idea to rewrite the database from scratch, from Go into Rust. And this,
okay.
So this is the version. This is we're selling a version of this as a distributed database, and we have in beta now a new open source release of version 3 and another commercial product based on that. But there were reasons that we decided to do the rewrite. So
tell me why you picked Go in the first place.
So this was the company started out as as a different company it was called Airplane, like ERRPLANE, like airplane. We just thought it was funny. Okay. And the idea for that product was essentially it was like a real-time metrics and server monitoring product, SaaS, like in the same vein of like Datadog and stuff like that. But this was in 2012. Okay. And to build that product, we actually had to build like a time series database. And initially what I used was like Scala on top of Redis and Cassandra. So Cassandra is the actual long-term data store, and Redis is like the real-time indexing layer.
Okay.
And in 2012, in like December of 2012, I was like, well, that infrastructure is kind of pain in the ass to deal and manage with. It doesn't have a bunch of features that I wanted to have. And also, I had this idea that we would want to be able to offer our software as like an on-premise solution. And there was no way in 2012, we were going to be able to ship, our Rails app, which is our front end, plus Scala, Cassandra, Redis, like all this other stuff. So I was like, I got to figure out how to and a MySQL database, right?
Yeah, that doesn't scream package me up as a single binary.
No. Although now there are people selling the dream that you could do that inside of Kubernetes and whatever, but that is a separate nightmare that I can talk about. But okay. I had this idea where I was like, okay, well, if I can take the time series portion of that and package up as one like thing, then we'd be able to, in theory, like ship this as like a managed service, because then we're just talking about a Rails app, this one thing, and MySQL. Fine, that would be possible. So Go had gotten to version 1.0 in March of 2012, and I thought the language was interesting. So I prototyped that backend in Go using LevelDB. LevelDB is, like I said, a log structure merge tree. It's written in C++. It came out of Google, written, I think, primarily at that time by Jeff Dean and Sanjay Gemalot. I just prototyped something, and I found that it was like was able to get like really great performance, like with very little effort, right? Just on my own, doing like a couple of weeks of hacky work. Right. So we rewrote the backend for Airplane in that. And launched that into production in early 2013. At the same time, we were going through Y Combinator. Went through 2013. I raised a seed round of funding for this company, for Airplane, and realized by the fall of 2013 that this just was not going to take off. We were not going to be successful with this idea. But I thought the infrastructure that we had built was super interesting. Okay. And I was like, well, we actually had on our Y Combinator application, like, they have the question, which is like, what would you work on if you weren't doing this idea that you're submitting with? And what we put down was open source time series database, because I was absolutely thinking of it at that time, because in 2010, I had worked at a fintech startup and I built a time series solution for financial market data. And then when we did Airplane, I had to build basically the exact same solution, but this time for server monitoring data. And I was like, okay, there's a common abstraction here. Yeah. And I think it's time series. And I also said open source because, it's 2013, 2012, 2013. And I'm like, if we're going to build a piece of infrastructure software, there has to be some core part of it that's open source. Otherwise, nobody's going to care. Nobody's going to do anything with it. Yeah, and this was before it was like accepted wisdom that all database workloads were just going to be SaaS in the cloud managed by somebody else, right? Yeah. So in the fall of 2013, I was like, okay, let's focus on, maybe we should try this open source thing. Maybe we should try this time series database thing. And we're like, we can't just like take the bits that we had written for Airplane and just like open source it. That's not going to work, right? We had never designed it with that in mind. I was like, but all the ideas are good. So we can do that. Plus we can do a couple of other things, right? That thing had like a REST API on it. And I was like, okay, well, it'd be better if it had a query language. And if that query language looked kind of like SQL, people would think it was like friendly and approachable and whatever. Yeah. Right. So that was the first thing the change that we had decided on. And then the next point of debate was, this is September of 2013. And essentially at that point, Rust was not far enough along. It wasn't even really on my radar at that stage. It was another couple of years before Rust would even hit 1.0, and async stuff didn't even really land for real until like fall of 2019. So basically the debate at that stage was, do we write it in C, C++, or Go? And all the three of us working on it at the time, we had the most familiarity with Go. We had all done C or C++ to some bit, but never like a ton of it professionally. Like at that stage, I think, I had written maybe like 20 or 30,000 lines of like C and C++, not that much. And we were just like, okay, well, if we do it in Go, what's the biggest risk? Our biggest risk at that time that we were worried about was the garbage collector, right? We're going to write a database project, and garbage collection is like, it seems very bad. But I was like, well, people have written some successful databases in Java, and Java has a garbage collector. So if they can figure it out in Java, certainly we can figure it out in Go. And the bet we made was that, we thought we can move faster if we do it in Go. And Go seemed like in 2013 that had some real momentum. It was really going to start picking up steam. And we just thought, it's probably going to get better over time, and we'll be able to just piggyback on those improvements. So let's just do it and Go, because our biggest risk right now is like, we need to make a piece of software that anybody in the world cares about. So, the risk is we don't ship anything that anybody cares about. It's not that it's not performant enough or whatever. I mean, although performance is very much like the reason why people would care, we already had enough evidence that would work well enough. So we're just like, we're going to do it and Go. And I would say for those first, 3-4 years of Influx as a project, I think we really benefited from the fact that it was in Go, right? Like, we were able to speak at some conferences and get some visibility. And we were also able to hire in people that, they wanted to work in Go. And we could hire in some great developers who were really like excited about being developers, which are the people you want to work with, I think, as a developer. So that was that. But in 2020, so fast forward,
when did the dream die?
Yeah, well, it's not that the dream died. Go is still a fantastic language, and there's still things I love about Go that I think are hands down it beats Rust, right? Learnability and compile times, it's not even a debate.
Okay.
Right? I don't think any reasonable developer can disagree that those are better in Rust, but maybe I'm wrong. But
I'm sure the internet, you can always find someone to disagree, but I'll go with the general principle.
Somebody would take the other side of that argument, I'm sure. In 2020, so I first started getting interested in Rust in 2018, and I took the time to learn it in the fall of 2018. And I picked this project of building your own programming language, like a parser and all this other stuff as a fun project to learn it. And I wrote this blog post about Rust. And at the time I thought this language is super interesting. It has all these properties that make it great. I did think it was an incredible pain in the ass to learn. It had been years since I had been that frustrated as a programmer trying to learn something. And it took me multiple attempts, a long, long time ago, to really learn how to write code. I think I had probably made 2 failed attempts before I actually really started to get it. But, those 2 failed attempts were in high school or middle school.
Right, yeah.
When I was trying to learn C++ off of this Learn C++ in 21 Days book or something like that.
Yeah. You do get this thing though, don't you? Because a lot of programming languages are roughly the same. And so when you pick up a new programming language, it comes very easily. There's not a wild amount of difference between learning Java and learning Python, I would say.
Right.
So you can pick it up, and then you come to a language that is quite different, and the hill suddenly hits you in the face.
Yeah, I mean, to me, at that stage, I had felt okay, there were probably 3 different learning curves for programming languages before I'd experienced Rust, right? And those learning curves, I think, are basically static typing and object orientation, right? So Java, C#, whatever. dynamic languages and duck type languages like Python and Ruby and JavaScript, and then functional languages. For me, my only functional exposure was essentially Scheme, which I just learned as like a nerdy exercise, not to actually do anything real. So most of my exposure at that stage was either in C# or Java or Ruby or JavaScript, right? And then obviously Go, which I just view as like another, statically typed language that's actually simpler to learn than Java or C#. So
you get to the point where you're over the learning hurdle of Rust and you're liking it. What happens next?
So then 2019 comes, and essentially, like at this stage, our business, 2019 is in the fall of 2019 is when we launched the first part of version 2. But our business at that stage was really all version 1 of InfluxDB. And we had and like I said, version 2, from a database perspective, the core elements, the underlying like core implementation of the database was the exact same. We used all that same code. So like there were problems related to the database that people wanted us to solve. So 2019, we launch version 2 with this new language. And we start getting a bunch of feedback on it. And a lot of the feedback is very negative about the new language, right? People don't want to learn our new language. They think it's dumb. They're like, we want to either use SQL or InfluxQL, which looks kind of like SQL for querying. And we want to use whatever programming language we're going to use for our programming stuff, which is not an unreasonable thing. Now, but the more important things, I'll set the language thing to the side for a second. The other important things were really like core database performance property things. So the biggest problem was what I call high cardinality data, right? So essentially, like, as I mentioned, you have the tags, which are basically, it's metadata that describe your time series. So cardinality basically refers to the number of underlying time series you have in the database. How many individual unique time series do you have stored in the database? And like I said, in some database formulations, you actually don't store those time series ahead of time, right? You actually produce the time series on the fly from the raw underlying data, right? You could take just a raw log file and process it into time series, right? Yeah. And you could actually build a query language that just does that, right? Loki's query language does that. It basically, like, you can construct time series on the fly. So our part was all the underlying time series mapped to actual unique structures in the underlying storage. So as the number of time series exploded, everything became more expensive, right? So reorganizing the data in TSM files became more expensive. And then the bigger problem was the index became super expensive. So where you have tag key value pairs, the number of time series that expands over time, or the number of unique tag values you need to track in your index. And as that gets bigger and bigger, it gets more expensive. And if you have data where there are a lot of unique things, then your index ends up becoming even larger than your raw time series data, right? So a great, degenerate use case is tracing data. Right? Tracing data, you are frequently pulling time series out of tracing data. But if you're to keep it in a strict time series format, right, you'd have the trace ID as a tag, and you'd have the span ID as a tag. And what that means is for every row that you write into the database, you're writing a unique span ID at the very least, a unique trace span ID combination, right? Because that represents one point in time, and it represents a time series with only one data point in it. And then, like, obviously, when you query, you're not querying for a specific span. You're querying for, give me this trace, or give me some aggregation of the tracing data across this. Doing that with the tag structure was you literally couldn't do it, right? So
I can see the index exploding on
and
that.
There are other use cases where it's not as extreme, but it does become difficult, right? Like, say, a process ID, or a container ID, right? Like you spin these up, they're going to run for some period of time. It could be minutes, it could be hours or days. And that is actually a legitimate time series. And the problem is the number of those expands over time, and it just becomes this like super expensive thing. So we had to solve, how do we store data where we can yield time series from it, where the underlying data could have effectively unbounded cardinality. Right? Which that's something we wanted to solve, because InfluxDB, like my vision is not that like we're creating a metrics database. Metrics is interesting, but to me, that's a subset of what's interesting about time series data. Like ultimately we want a database where you can store literally any kind of observational data about the real or virtual worlds that we create, right? In servers and software and whatever, real world sensors, machines, anything out there in, our physical reality. You can store all of this kind of data and you can execute queries against it and get time series back, right? That's where I want to get to. But having this underlying structure meant there was no way it was going to work for all those varied use cases. And we had customers and users telling us we need support for infinite cardinality. Now, it's not everybody, but it's a very large, vocal group of people. And then one of the other problems we had to solve for was, how do we keep historical data and not have it be super expensive, right? So InfluxDB 1 and 2 required you to have a locally attached disk. We told everybody the best thing to have is a locally attached SSD drive, right? And the problem is, like I said, the data that you query, like, most of your workload is against this very recent data, and you want to be able to query the historical data for ad hoc analysis or whatever, but that's a tiny fraction of your query workload. And to have your massive amounts of historical data have to be stored on a locally attached SSD is super expensive. So people wanted object storage. They want to be able to have historical data in object store and all this other stuff.
I can totally see that you want to offload those 7-day chunks you were talking about to S3, right?
Exactly. But still have them be accessible. And then the other big part was people wanted query language that they knew, so Flux, we still run and operate Flux. We still have customers on version 2. We have a partnership with Amazon where they host open source version 2, and they now host another commercial version of version 2 that we launched with them. So we support Flux still, and Flux has a group of people, a minority, but a group of people that are very enthusiastic about the language and what it can do, right? Because like I said, it's a scripting language that gets executed inside the database. So you can do a lot more things than you can do with just a basic declarative query language like SQL. But by and large, the majority of people responding to version 2 of InfluxDB wanted either InfluxQL for like simple queries where it made sense, or they wanted full SQL. They want a full SQL engine where they can do joins, they can do all these other, windowing and partitioning and all this other stuff. And when I looked at, okay, we got to solve the cardinality problem, we got to solve the object store problem, that basically means we're rewriting the storage engine. We got to solve the SQL query problem, which means we're rewriting the query engine. I'm like, if we're rewriting the query engine and the storage engine in the database, that is a rewrite.
Okay. So totally. I'm not sure I see I would be very wary if I were in that situation of rewriting both at once in a different language.
Yes, that is true. And again, if I were to go back to Paul at the beginning of 2020, I would tell him to do it a different way.
Okay. So let's start with the decision you did make. I want to know the benefit of hindsight. But so you chose to rewrite the whole thing as a big bang in Rust?
Yes. So again, like I chose Rust because it was 2020, and the async await stuff really landed in the fall of 2019. At that point, I'm like, okay, Rust is going to be good for server-side software, right? The performance is great, zero cost abstractions, great error handling, fearless concurrency, cargo, and the package management system is great. I guess Go has solved that problem, but like I stopped doing Go in like 2016, and at that point it was still very much a nightmare.
Okay.
So yeah, I thought Rust was a great language, and then the discussion was, well, and why would I do that versus just doing it in Go? Well, one, like not having a garbage collector and being able to optimize everything we wanted to optimize to whatever degree we want, to me was very appealing. Those other parts of the language, like the fearless concurrency and the error handling, were also appealing.
Had you hit the point where the garbage collector was a genuine problem?
There are a bunch of places where it was potentially where it could cause problems, basically.
Right.
I mean, again, like we could have continued working on the Go code base and making improvements, but I thought, well, if we're going to rewrite the entire thing, like I want to use what I think is the best tool in 2020 for this job. And I think Rust is a better tool for this. Like if I were to like just start a fresh project from scratch right now to build a database or a piece of high performance server software, I would do that project in Rust. There's no other language that I would choose. Okay. And again, like it's debatable about whether or not the benefits were big enough to warrant making the switch. But I felt there were. The other part of this was we needed a query engine, and I did not want to write the query engine ourselves. Right? We had done that with version 1 with InfluxQL. We did it all over again with version 2 and Flux. And with Flux, we actually wrote not just a query engine, but we, with a planner and optimizer and execution, we also wrote a scripting language. Right? So it was a whole bunch of stuff. And I was like, we're not going to write our own query engine again. We're going to pick something off the shelf. And at that stage, I was fairly certain that the query engine we picked off the shelf would be written in C or C++, because it would come from an existing database, right? Because we needed SQL. So it was going to come from an existing database that supported SQL. And we were just going to rip their query engine out and put it in here. And I thought it was going to be I thought it was going to be in C or C++. And like one of the first jobs of like, initially this started out as like, it didn't start out as like, we're going to rewrite the entire database and this is going to be version 3. It started out as we're going to rewrite the storage system, bring that into the Cloud 2 product. And we're going to also like use this query engine on top of it. So one of the first bits of research was, what query engine are we going to use? And in June of 2020, Andrew Lamb joined us in May of 2020. And one of his first jobs was to look at what was out there and see what we should use, right? And we looked, he looked at ClickHouse, DuckDB, and DataFusion, right? And in June and July of 2020, there was no ClickHouse company. It was basically just some project that had been open sourced out of Yandex, and it didn't have much traction or visibility. DuckDB, there was no DuckDB Labs, there was no Mother Duck, there was no company at all. It was basically just some postdocs from CWI hacking together this project.
Right.
DataFusion had been donated by Andy Grove to the Apache Arrow project in the fall of 2019. And basically, like, that code base was largely just written by Andy and nobody else. So these were, I would say, from a maturity perspective, ClickHouse was the thing that was furthest along, but it lacked some things that we felt we needed to make the time series use case work well. And basically, when we looked at those 3 projects, we realized, well, whatever it is we pick up, we're going to end up having to contribute to and own it in a very significant way, right? Like, it's not going to be something that we can just use and like forget about and it just works, right? Whatever it is. It's going to
also be the thing that DataFusion's the only one on that list which is intended to be embedded in other things.
Yes. Yeah. So DataFusion was appealing for 3 reasons. One, because of what you just said, it was intended to be used as basically a library, as like a toolkit for building a database, right? Because it's got the parser and the query engine, planner optimizer, whatever.
Yeah.
So it actually had a structure that lent itself to that. The other was that it was written in Rust, whereas the other two are not, right? The other two in C++.
Yeah.
And then the last bit is basically governance. It was under Apache. So we knew, like, it would, I didn't know in like DuckDB Labs got formed, I think in like August or September of 2020. I didn't know in July of 2020 that was going to happen. ClickHouse, the company, I don't even know when that started, but it was a while later. It may have been in late 2020 or 2021. I don't remember which, but definitely at the time, ClickHouse, the company, was not, at the very least, it was not a public thing that was a thing that had happened. So having it be in the Apache Software Foundation was appealing because we were like, okay, again, like the view we had is like, we don't want to write our own query engine, but we're obviously going to have to contribute to one very heavily in order to get what we need.
Yeah.
But essentially, like, you can think of the query engine as a dependency that we have. It's a dependency to deliver the ultimate product we want to deliver. And one of the best use cases for open source is to commoditize your dependencies. You want your dependencies to be as cheap as possible, as widely used as possible, because the more use they get, the more robust they become, the more reliable they become.
The more chance ideally, that the feature you're looking for has already been done for someone else.
Exactly. Yeah. So we're like, the query engine is a dependency for us. It's not actually where we like make our money or add our unique, benefit to the world. It's just a thing that we need in order to deliver this like other larger database and service.
Yeah.
So having it be Apache, we thought, okay, if we start contributing to this thing and we use it in our project, ideally, like we can promote that and it will build up momentum over time and people will contribute to it. So that's how we landed basically with Rust, with DataFusion. We picked Arrow. Arrow is obvious because like DataFusion uses Arrow. So we use Arrow internally as the memory-based format for a lot of the data. We also landed on Parquet as the file format for the data. And again, the reason we did that is because we thought, okay, what we want actually is a database where compute is separated from storage and storage is object store. And we want to keep Parquet files in object store. And the dream that we had at that stage was if they're Parquet files in object storage, we get really easy integration with downstream third-party services, right? Like is our focus is this like real-time time series database use case, largely against recent data. But we want to make it easy for our customers and our users to access that time series data in large scale data warehouses and query systems like Athena, Snowflake, Databricks, whatever. And we thought, if we have it in Parquet and object storage, people are just going to be able to like pull from those other things.
Yeah. The standard will work for you.
Yeah, that isn't reality, the reality that we've experienced, but that was the dream.
Okay, now we've got to go down that side road quickly. Why does that dream not work out?
Because there are all sorts of different pieces of Parquet of the format, and not all downstream readers support all pieces. So for us, most specifically is nanosecond timestamps. Nanosecond timestamps are supported in Parquet, but downstream people don't really support it. Iceberg, for example, the initial Iceberg spec did not have support for nanosecond timestamps. They had support for microsecond timestamps. We added support to the Iceberg spec for nanosecond timestamps, but that has yet to thread its way through all of the downstream Iceberg implementations and places where you'd want to read Iceberg. So what it means is the Parquet files that we write right now, the default format, is not actually readable by all downstream third-party providers, right? If we want to make it readable by downstream third-party providers, we have to rewrite that Parquet file into a slightly different Parquet file so that it can be queried by downstream providers, right? So that's the problem is like, yes, Parquet is a standard, but it's like SQL is a standard. And there are all sorts of different flavors. And depending on how you do the integration and where right? This will change over time, particularly I think as more people adopt Iceberg and build around it. But I think that process is going to take years, right?
I can see the dream is slowly loading on that front.
It is, but the question is it actually an achievable dream? Or is it basically just a red herring where people want a thing to be true, but ultimately it's not true, right? Like the dream of write once, run anywhere, or whatever.
Oh, yeah. The thing that Java World stopped saying after a few years entirely, right?
Right.
Yeah. Okay, let's come back out that side, Ali, because you from the rewrite into Rust looking like a desperately risky thing, I can now see why at the time you were thinking, okay, we'll get the query engine largely for free, we'll get standardized data format for storage and object storage largely for free. This suddenly doesn't seem quite so risky to rewrite entirely in Rust.
Yes.
But you in hindsight, you regret going down that path. Why?
Well, so again, like the plan, and this was in 2020, the plan was we're going to rewrite it as the backend storage system for our Cloud 2 offering. And at this stage in the company's evolution, we very much thought that our Cloud 2 offering was the future of the company. That's where everybody was going to go. Everybody was going to use it. And over the course of the next year and a half, we learned some really important business and technical lessons.
Okay.
So our Cloud 2 product is like there's open source version 2 of InfluxDB, which is written in Go. It's this all-in-one thing. And it basically has a user interface. It has the background processing engine, tasks, and it has the query engine and like storage and all this stuff, right? It's just like you go, you install that, you run it. Now, the commercial version of version 2 is a cloud SaaS product, and it's comprised of a bunch of different services, and the whole thing runs inside of Kubernetes. And it's a very complicated thing. And it uses bits and pieces from that open source version 2, but largely it is a completely different database and a completely different implementation, different architecture, and it serves the same API and the same UI plus a bunch of additional UI features that only make sense for our cloud offering. So what that means is we were writing 2 databases, one that went out as open source and free, and one that was as a cloud product. And the problem is the architectures of those 2 databases were completely different. So the performance and operational characteristics of those 2 databases are different. And this is kind of unavoidable given the design of the 2 things. Now, this creates a problem as a business because everybody who starts, go back to 2020, 2021, 2022, any one of those 3 years, anybody who starts with InfluxDB downloads the open source thing, they use it, they love it, they say, oh, great, I want to go to the cloud hosted version of it, and they move over, and basically there are some performance and capability differences between the thing they played around with in open source and now the thing they're paying for. That's one.
Yeah.
2, the cloud hosted version of InfluxDB is usage based, right? And we really wanted to get to usage based because we thought, 1, we can offer a free tier pretty easily on that. 2, we can charge people. So you pay for data in, right? In terms of bytes of data in, you pay for data at rest, you pay for number of queries executed, and you pay for data egress. But that is just like a price forwarding from like what we get charged by the cloud provider. We just charge you whatever the cloud provider charges us for egress. Now, on the query side of things, we actually didn't start with number of queries. We originally started with compute time. Basically, query like the amount of compute time that the queries that you executed used.
Makes sense.
And people hated it. They couldn't understand it. They're like, I have no idea how much this costs. Like, I'm not going to buy this. So we changed it to query count. And basically, when you change something, so the truth is, like, the compute time metric is the fairest metric on which to bill, because that actually represents the amount of our resources that you used that we ultimately have to pay for.
Yeah.
If you switch over to something which is a rough proxy for resources, what you have to do is you have to set a price that's actually more expensive, because an individual query could take 5 milliseconds, or it could take 5 seconds. So that delta is huge, right? There's a massive delta in terms of the amount of compute that you use for a query. So if you're just going to bill on query count, you have to make sure that you make the queries expensive enough so that you make
to absorb
up for
the cost of the more expensive ones.
Exactly.
Yeah.
So what it means is it's basically a less fair way to price, but people prefer that way because they find it to be more predictable, because they can easily back into, I know how many queries per second I'm going to send to the service, and then I can figure all that out. And what that also means is the pricing doesn't look reasonable when you run a open source InfluxDB 2 instance on a cheap VM, and you're like, this thing can do all this stuff for a fraction of the price that your cloud service is advertising, right?
Oh, yeah. Oh, so, that's really thorny from a technical and a business point of view.
Yeah. So, I mean, the truth is, like, the cloud service is doing a bunch of other stuff that, the open source InfluxDB running on a VM isn't doing. It's providing backups and monitoring. It's highly available and all this other stuff. But at the end of the day, when developers are looking at it and they're evaluating it, if the price delta is too high, then they're like, this is crazy. And what we found, this is maybe too in the business weeds, but what we found was that as customers get larger and larger, price predictability matters more than price fairness, right? So what they want, as you spend more and more money on a solution, you want predictability. You want to be able to say, I'm doing my budget for 2025 or 2026, and I'm going to allocate X number of dollars to this solution, right? So you really don't care about usage-based pricing. You care about price predictability.
And you don't have the time to dive in and optimize individual queries, which a particular developer might.
Right.
Yeah, so it makes perfect sense.
What they preferred from a buying perspective, larger customers, what they prefer from a buying perspective is, just tell me how much infrastructure I'm going to need, and I'll budget for that infrastructure, and we can go from there, right? They don't want to do usage based. Now, of course, they deal with usage based with Amazon and Google and in Azure, but that's a totally separate thing, right? There's a whole cottage industry around optimizing your spend in the cloud providers. Because of this. So basically, but again, going back to 2020, our view within the company was like, Cloud 2 is going to be the future of the product, and we are going to build this new storage system and put it into Cloud 2, and the new storage system will bring about those 3 things, right? Infinite cardinality, cheap object storage, and a SQL engine so that people can do SQL queries.
Yeah.
And now we get into the technical lessons here. So we implemented essentially the storage system based on Parquet and object storage and whatever. And we implemented the SQL engine. And within our Cloud 2 offering, the storage system is run as this service, and it has this gRPC API that it exposes. And the gRPC API is essentially, it's not like a full query API. It's basically like a limited, give me the data for this measurement for this tag set, and then it'll push down aggregates, right? So it has some sort of push down. But then the actual bulk of the query processing happens in a Flux engine, which is in RAM as a separate service, right? Okay. So what we did was, we at this stage we're like, we have to support Flux, we have to support InfluxQL in Cloud 2. Those are 2 separate services written in Go. And what we're going to do is we're going to replace the storage service, right?
Yeah.
So everything in Cloud 2, all that other stuff, that's still going to be written in Go. Flux is going to be there. InfluxQL will be there. That's all in Go. And we use this storage system. And we implemented that gRPC API, which used DataFusion to query our underlying thing. And we deployed this. And then we didn't deploy it for production for customers. We deployed it in an environment, and we mirrored production workloads from existing customers of our Cloud 2 product, right? We mirrored it over the write workload, the query workload, all that stuff.
Makes sense.
And what we found was that the performance was absolutely abysmal. It was so terrible. It was so bad. And the reason was, so one, like, people wanted infinite cardinality, but that's not how they were using the product. And there was another piece of this that I forgot to mention, which is our customers have long been asking for the ability to do analytic style queries against time series data. So I mentioned, like, the time series queries are largely like, give me the values for this time period for this time series, or this few dozen time series, or compute it across these 2,000 time series, compute some sort of aggregate, right? But it's basically all limited by these individual time series. Yeah. They also wanted to be able to do, and InfluxDB 1 and 2 are terrible at this. They wanted to be able to do like a fleet-wide calculation of, like, you know, give me the 10 highest CPU load servers across the entire fleet over the last like 30 minutes. Right. InfluxDB 1 and 2, if you have a large enough fleet, it just won't, that query won't return, or it'll like the database, or it'll be like absolutely terrible. Right. And again, that's because of how the data is organized and how the query engine works to like do the time series thing. So those kinds of analytic queries, more and more of our, particularly again, our larger customers were saying, we need to do these kinds of queries. We need you to help us do this. So we need infinite cardinality. We need these analytic queries to be fast and whatever. And basically what we had built with this first, part of the storage engine replacement was infinite cardinality, check. Object storage, check. SQL query engine, check. And analytic queries are super fast, right? When we benchmarked analytic queries versus version 1 or 2, some queries were like literally 10,000 times faster. It was like completely insane, right? And we're just like, this is great. And we do the production mirroring, and guess what? Like, none of the workloads for our current customers have those properties. None of the workloads care about those things. All of the workloads care about the things that version 1 and 2 are actually good at. The things that they were optimized for. And again, like, I did not appreciate this going into, this is one of the reasons why you don't want to do a full rewrite, is because you solve this classic problem where you solve for the problems you see everybody mentioning, and you forget about the problems that you had already solved. And you don't. So basically, we created a solution for this set of problems, but we didn't also solve the previous set of them.
Yeah, you didn't carry across your history of solving difficult things.
Yes.
Yeah.
So
ouch.
Yeah. And I will say, I do think those two workloads are probably at odds with each other in terms of like how you execute against them. I'm starting to believe that you actually need to keep 2 copies of the data optimized for different styles of workloads, but that's a totally separate thing. So yeah, we learned that lesson. And then basically by 2022, by the summer of 2022, the business lessons of the Cloud 2 product were becoming obvious, and the technical problems were becoming obvious. So basically it was all coalescing into this. And
had you launched at this stage, or did you hit that point and realize, we can't actually ship this?
We had not launched at this stage. No, we were still very much in development. And at this stage, the people working, so 2020, it was me, this guy, Ed. We started initially on the work. He was one of the core engineers on version 1 and then on version 2. So he was like one of the core database engineers. And so the two of us started on the work, and then Andrew joined us in May of 2020. And then by November of 2020, I'm like, okay, we had selected the technologies like Rust and Arrow and DataFusion and Parquet. So I'm going to give this talk in 2020 about how we're building a new core engine of the database. We need Rust developers, right? So the idea was we can actually get people interested. And we had, I think, how many was it? Like 5 people start in early 2021, and we brought over a couple of people from the existing team. So by March of 2021, we had, I think it was a total of like 8 or 9 people on the project out of a team of, at that stage, I think we were like 70 developers or 75 developers. Okay. So that's the level of like investment and work we were doing. All those other developers were either working on maintaining and improving version 1 or working, most of them actually, on version 2 and the Cloud 2 version, right? So we had 8 people working on this thing for multiple years in isolation. And then finally in 2022, in like June of 2022, we deployed it into, the cloud and started mirroring the workloads, and then like realized like it's not working.
Ow.
So, but the other thing that became apparent in the summer of 2022 was that we had mispriced our Cloud 2 offering, and it was horribly inefficient. So there was a period of time where we were actually at negative margins for our Cloud 2 offering.
Ouch.
Yeah, which is the worst possible thing. And again, like I guess the other technical lesson we learned over this time was like a multi-tenant service is a terrible idea for a data plane. A data plane should be single tenant. I'm just going to stick to this. It depends on the complexity of the data plane, but the more functionality you add into the data plane, the more important it becomes for it to be single tenant.
Why is that? What's so hard or so much easier with single tenant? Is it just trying to manage different fleets of what should be the same software but isn't?
So there's the noisy neighbors problem, as always. There is so why I mentioned the complexity of the service, right? Like if you think of S3, like particularly what they started with, right? You had get, put, delete, and list. And there were a lot of like guarantees that weren't provided, right? Just because you did a put on something, if you did a list, it may not even show up, right? There was no strong consistency there, right? And basically what it meant was there is a very limited set of things that you can do. Like somebody can't submit a query to S3 that causes the system to like go crazy and do a bunch of work that you didn't expect, right? At least with that. For the services layered on top, you can get to that, right? Like a Athena or whatever. But that's the point, is those are separate. And those run in their own separate VMs, apart from the underlying data plane, which is the simplest possible thing you can imagine. And what we had was, in Cloud 2, we had the shared data plane. We also had a bunch of query servers, and we didn't separate out who got what. So you had noisy neighbors problems. You had the problem where the largest customers actually want dedicated resources, and they want price predictability. So they want to be able to say, look, I'll just pay you for 50 VMs that you're running for me, as opposed to paying on a usage base. And we had built the whole service as this, like, everybody's in anything, and it's just like a bunch of different, they're all getting multiplexed onto the stuff.
Right, yeah. So it was mostly quality of service issues.
A lot of quality of service issues. Yeah, okay, a lot. Okay. Quality of service. And then, like I said, the other piece, which is large customers want to have their workloads separated from other people. One, because they don't want their data mixing with other people. But the other is also because of like quality of service, and then finally for like the idea of like reserved instances and reserved pricing.
Right. Yeah. Okay. So you're at this stage where you go on.
Yeah. So basically, in the fall of 2022, we realized we had to like restructure the company. We ended up doing a layoff in the fall of 2022, which a lot of people were doing at that time.
Yeah.
And at that stage, we were like, okay, we're going to try and we've been working on version 3 for whatever that was, I guess 2 years, almost 2.5 years, right? We're like, we need to get a version of it out. So we are going to deploy it as part of the Cloud 2 service. And we realize like the Cloud 2 service, like we're going to keep operating that for our customers who are running it, but we're going to change it up so that it's now going to be based on this new storage system. We're not going to migrate those people over, right? Because we already established that the performance is not the same. But we're going to run it as essentially a new service and a new product that people will hopefully sign up for. And then they will have usage that maps to what it's good at, right? Those analytic queries against very recent data, time series data is still very, very fast and good, right? It's more like the query of, oh, give me the last 5 days of this data, or go a week in the past and give me 24 hours of this data, right?
Right.
The single time series, not all the single time series queries are nearly as fast in this version of version 2, the version 2 cloud, which is still running today, and we're taking signups. That's called cloud serverless. Right. It's serverless because, again, it's like this multi-tenant thing.
So is the current state of play right now that you've got 3 different versions out in the wild that you're still maintaining?
That's right. Yeah. We have customers on every single one of them. So, and that's going to continue to be true for years, for sure.
Okay.
The thing is, like,
painful.
It depends. Like version 1, it's not really painful. We have like a small team of people who are really familiar with the code base. They're able to operate it. They're able to help with, support and stuff like that. The customer base that we have on that, like, they largely are settled in on their use cases. And we actually still sell version 1 enterprise and version 1 cloud for customers where it makes sense, because we're still not at a point where the version of version 3 that we have is better at everything, right? The vision here is we get to a version 3 InfluxDB that is literally better at everything than version 1 and version 2. We're not there yet. We will get there. But in the meantime, version 1 and 2, like, they're actually really good for some things. And we're going to continue to sell those to customers who want to run it. And we're going to continue to operate it, right? Like, if the unit economics work, there's no reason not to continue to run and operate it, which they do. Thankfully, our margins on Cloud 2 are no longer negative. they're positive. So we fixed that problem. But that was the thing, is like, one of the motivations for moving the version of version 3 that we have into our Cloud 2 product as the back end was it's much more efficient economically, right? It's much better in terms of cost for the workloads that it services than our version 2 database, right? The version 2 database does all this crazy indexing, and it has to have locally attached EBS volumes with provisioned IOPS and blah, blah, blah. Like, it's basically more expensive. So because of that margin problem, we're like, well, we got to get this new version. We got to just like switch over to the new storage engine, even though it doesn't have all the things we want to have right now. And we need to get it launched so that every customer we're signing up isn't costing us money. I mean, there were other problems that were basically non-technical, like business related problems, where we were cutting like really big discounts that we shouldn't have been doing. And, like all sorts of like really, really lame business stuff. But
yeah, the realization that when you're building a tech business, you're not just building tech, right? You've got to build the business systems, and they're hard and ambiguous and painful to change relatively.
Yeah. So fast forwarding a bit, like, we then launched a version 3 product called Cloud Dedicated in late April of 2023. And what that is it's a single tenant service. We run this. Now, this version of version 3 is like a distributed database. It's all written in Rust. It is separated out by a set of services that run ingest, query, compaction. It uses object store. It also uses Postgres as like a backend catalog system.
Interesting.
It's like a complex, like services-based piece of software. But when we launched that, we said we're going to launch this as a dedicated offering, right? So what that means because it's such like a complicated piece of software, like the minimum footprint, the minimum viable footprint of it is actually quite large. So we actually only talk to customers who are going to be spending at least like $40,000 or $50,000 a year annually. And we don't have any sort of like self-serve, I want to try this out, right? If you want to try our cloud dedicated product, you have to talk to our sales team. You have to like go through this like proof of concept and all this other stuff.
Yeah, that's probably the big downside of single-tenant, right?
It's a painful thing. There are ways to do single tenant where you don't have to do that, but we were not able to do that with this particular release of version 3. Mm-hmm. So at the beginning of last year, I peeled off from that team to form a new team to work on a much more simplified version of version 3. And the goal was to have a single server thing that could operate with zero dependencies or just with object storage. And it would be easy to deploy, easy to use. There would be an open source version and there would be a commercial version. And then this kind of evolved over the course of the last 15 months of development, where I realized, well, if I'm going to use cloud storage as the storage piece, we can actually create a distributed version of this simple version 3 product that is based on what people are now calling like a diskless architecture, right? So WarpStream, the company that built a Kafka competitor and then later got acquired by Confluent, did this. The people who started WarpStream actually did this in a project at Datadog called Husky. So the idea is essentially you can use object storage as the distributed system primitive. So you actually don't have to worry about how do I do replication? How do I do consistency? All this other stuff. You just have object storage and you can operate multiple servers, and they actually don't have to communicate with each other. They can just share data through object storage. So the version of version 3 that I've been working on for the last 15 months with a small team of people, we just launched the alpha of that in January. We launched the beta of it about 3 weeks ago. And we'll launch the GA of it later this month. So that is basically open source version 3, which is still MIT or Apache licensed at the user's choosing, like things are in the Rust ecosystem. Yeah. Or this like commercial version of it, which offers high availability, scale out query workloads, extra security, and all this other stuff.
Do you think eventually you'll decompact this to a single code base?
I think so. Yeah. I will say the version of version 3 that this thing that is currently in beta, the vast majority of the code from it is actually code from that distributed version that we run right now in production. Right. So basically we took all of that code and we're using it. We just created some additional pieces and changes in it so that it could be operationally much simpler and have this like diskless architecture. But
so it's more of a branch than a fork.
Yeah. Okay. I mean, eventually like these things will all converge onto one thing. There's some other big things that we're working on this year that will be after the general availability release, that will actually bring, the same performance, really good performance capabilities that version 1 and 2 have into this version, along with infinite cardinality, analytics queries against high cardinality data and object storage and all that stuff. So
yeah. I wasn't expecting us to talk quite as much about the ups and downs of the business side. but that does lead me into another interesting thing about you that I did want to ask, because a lot of us on a career trajectory through tech, we get better and better at tech till we're promoted into management, maybe start our own business. But if you do that, then you really go into management and you get trapped in being a manager when what you really are or want to be is a techie. Seems to me you've done quite a good and deliberate job of avoiding that.
Yeah, so it's changed over time. Like, so I would say interestingly, like I hired in Evan as the CEO. He joined at the beginning of 2016. And I would say by middle of 2016, I was writing almost no code. And most of what I was doing was actually managing, like, and talking to our developers and talking to customers and users and stuff, and trying to come up with like improvements to version 1, and then coming up with a vision for version 2 and ultimately version 3. So there was a period, I would say, from like mid 2016 to, early 2020, where I wrote very little code, and most of what I was doing was, managing, not like as a manager of a development team directly, but like managing the managers, and like trying to come up with like how are we sequencing the work, what are we working on, talking to customers, talking to prospects, a lot of like sales and pre-sales work. And going out to customer sites and meeting with them. And then I would still do a little bit of development in my free time. Like when I learned Rust in the fall of 2018, like I did that in my free time. I did that off work hours, right?
Yeah. I've been there, where you reach the point where you're craving writing some code. Just any code, please give me a keyboard again.
Yeah. So, and basically in the fall of 2020, I decided, you know what, I actually need to pull back and start writing some code, because I felt then that we needed to really focus on making some core database advancement, and all of our focus for the last year or so at that point had been on higher levels of the database, like other things. I was like, well, I'm not going to be able to like manage this process of building out this new core of the database if I'm not like actually in the weeds doing work on it. So that's when I started getting more and more involved. And then over the course of that initial development timeline, again, like it started out where I was like writing a ton of code. And then after, a year, we hired in a bunch of developers, and then I became more of a manager and like reviewing more code. And then gradually over time, I did less and less until we finally actually released it. And then when we released the first, the cloud dedicated product in April of 2023, I switched. I wasn't writing any code at all. Like the only thing I was doing was talking to prospective customers.
Right. You keep accidentally slipping up the mountain.
Yeah. So, and then again, like when it came time to start this new flavor of version 3, I was like, well, the only way I'm going to be able to do this is if I'm actually writing the code. And this time I deliberately kept the team small. I wanted at this stage, we were 5 total people, and we actually, for a while, we were just like 3. I believe basically in the early stages of a project, it's better to have a smaller team. I think even 5 is a bit difficult. Like, honestly, to me, early stages of a project, like 1 or 2 people is best. Then you add like a 3 and a 4, right? But like, I don't know. I think there's a process for like adding more people to a project. It's not like if you start a project and you have like 10 people on the project, it's like a kind of a nightmare. When you're just getting started out. So basically, like, I've been in the weeds writing a lot of code. I'm still writing a lot of code. But as we move into GA and more of that other stuff, I very much anticipate that over the course of the next 12 months, I'm going to be writing less and less code. I'm going to be doing more, speaking at conferences, talking to customers, talking to users. So it all kind of like ebbs and flows over time, I think.
Yeah, it sounds like you are at heart a builder and a startup maker, and you found a way to keep starting new and spearheading new projects, even within one large company, right?
Yes, but hopefully this will be the last one. I don't think I have the energy to do another startup database. So hopefully this is... Yeah, this is like the one time series database to rule them all. So we'll continue improving this one and keep it going. So
cool. Well, I wish you the best of luck with it, and I hope they eventually coalesce on a single glorious Git branch.
That is the plan.
You'll get there. Paul Dix, thank you very much for joining me.
Yeah, thank you so much, Chris.
Thank you, Paul. If you want to learn more about InfluxDB or you want to try it out with your own data, you will find links in the show notes. If you're ever tempted to build something similar, you might want to check out our previous episode on Apache DataFusion, which Paul mentioned. It's something of a database building toolkit, which makes projects like that a lot easier. Still hard, but much easier. Again, link in the show notes. If you've enjoyed this episode, please do take a moment to like it or rate it. It really helps other people to find us. And make sure you're subscribed so that you can find us next time. But until then, I've been your host, Chris Jenkins. This has been Developer Voices with Paul Dix. Thanks for listening.